I'm Ron Klaus here again. I'm calling this talk What Science Can and Can't Tell Us About the Universe. I've been interested in science and math ever since I was a young boy. I therefore decided to major in engineering, later worked for the U.S. space program, and eventually taught engineering. Even though my career later went in a different direction, I still maintain my interest. But my interest has gone beyond that to the question of how science affects our worldview. In this talk, I want to tell you something of a fascinating story about how science developed. It was not the neat, orderly process that some people imagine. It had its twists and turns. Despite their stated commitment to following where the data led them, scientists are humans, strongly influenced by their personal philosophies, sometimes resistant to what they find experimentally. So, here we go. The scientific revolution may be thought to have begun with Copernicus in the middle of the 16th century. Although there was a lot of thought about our solar system before him, it was he who made popular the idea that the sun was at the center of our solar system, not the Earth. Science reached another mountaintop through Isaac Newton, who through the middle of the next century published 3 laws of motion that are still the foundations of classical physics. Long before then, the Greeks had done some scientific inquiry. They were able to ascertain that the Earth was a sphere and even made a fairly good estimate of its size. But they believed that all truth could be discovered through reason alone. The difference between that and the later scientific revolution was that the scientific method was based on the need for experimentation to determine the truth. So, for example, the Greeks believed that a heavier rock would fall faster than a lighter one because that seemed reasonable. When I asked my young daughter what she thought about that, she at first agreed with the Greeks. That is, until on a small summer family vacation, we were staying in a cabin whose roof came down quite low. So I sat her down on the roof with 2 stones of different weights in her hands and had her drop them simultaneously. She was both surprised that they hit the ground together, but learned something through that simple experiment. You shouldn't believe something that you haven't tested experimentally. This is the distinctive element of modern science. The earliest modern scientists followed this recipe. Make observations, try to invent a mathematical theory to explain them, test the theory with further experiments, continue this process until you have a theory that's repeatedly consistent with experimental findings. A huge early success was Isaac Newton's 3 laws of motion, first published in 1687. They explained the motion of projectiles on Earth, but its crowning achievement was when it also explained the movement of the observed planets. However, one of its characteristics was that it predicted a steady-state universe. That is, you could predict the motions of objects into the future, but you could also determine their previous motions as far back in time as you like. Thus, according to this theory, no creator of the universe was needed. Perhaps it had always existed. This conflicted with Newton's religious commitment. He believed in God as the universe's creator, but it is to his credit that he stayed with his scientific discoveries, even though they seemed to conflict with his religious convictions. During this time of scientific development, there arose an interest in waves. Certain experiments showed that light was a wave, but that raised an interesting question. Water waves exist in water, air waves exist in air and produce sound, but if light is a wave, what's the stuff that's vibrating? No one knew, but they gave this mysterious stuff the name ether. That led to an interesting experiment done by 2 American physicists, Albert A. Michelson and Edward W. Morley, at what is now Case Western Reserve University in Cleveland in 1887. Without going into the details of the experiment, here's the overall idea. If you're moving a boat traveling into the wind, the water waves seem to be coming at you faster than if you're traveling with the wind. So these 2 hoped to determine the speed at which the Earth was moving through the hypothetical ether. The remarkable result was that no matter how hard they tried, they found that the Earth's speed through the so-called ether was 0. In other words, there was no such thing as ether. There were multiple repetitions of this experiment by many different people, all with the same results. And it leads to the unexpected result that light travels at the same speed in a vacuum regardless of your motion. This was troubling because it called into question Newtonian physics, at least at very high speeds, such as the speed of light. That got a young postal clerk, Albert Einstein, thinking about how Newton's equations could be modified to account for this. He succeeded in doing so, and in 1905 published what is called the special theory of relativity. This was a new question that superseded Newton's equations, but it reduced to Newton's equation at moderate speed, so it blended well into classical physics. Einstein was now on a roll. he tried to start thinking about gravity and wanted to understand it better. It was known to be a force, but it was not understood well beyond that. But Einstein was impressed by the similarity between gravity and acceleration. For example, if you stood on an elevator on a scale, you would have noticed that there was an increase in your measured weight while the elevator accelerated upward, and a decrease as it started to move downward. But if you'd come back to your normal weight whenever it reached the steady speed. This simple fact led Einstein to think about the relationship between acceleration and gravity. It took him 10 more years, but he was finally able to formulate and publish his general theory of relativity. He proposed 2 experiments that would either verify or falsify his theory. One was that his theory predicted that light rays would bend slightly if they passed through a sufficiently strong gravitational field. Another was that planetary orbits would be slightly different from their Newtonian predictions in a sufficiently strong gravitational field. Sure enough, the experiments were done. During a solar eclipse, the light from a star almost directly behind the sun was bent as it passed very near the sun at just the amount that Einstein predicted. Further careful studies of Mercury's orbit around the sun showed that it followed Einstein's predictions, not Newton's, and this was a huge triumph for general relativity. Despite its strangeness, it has repeatedly been verified, perhaps more than any other theory in physics. However, in Einstein's mind, it had one flaw. It predicted that the universe had either to be expanding or contraction. An Einsteinian universe could never be static. This troubled Einstein enough that he modified his theory by introducing a so-called cosmological constant. This fixed his theory so that it would predict the steady-state universe. He did this, however, not because he had any reason to do so, except his own bias in favor of a steady-state universe. Enter an obscure French priest named Georges Lemaitre, who also taught physics. He took Einstein's original theory and used it to predict that our universe was expanding at a rate that he determined and published. He met Einstein and tried to persuade him, but Einstein rebuffed him very strongly. He was still not ready to accept the idea of an expanding universe, even though his theory predicted it. Enter an astronomer named Edwin Hubble. He had the opportunity to do observations which was what then the most powerful telescope in the world, having a mirror 100 inches in diameter, situated at the top of Mount Wilson in Southern California. I met my wife-to-be in Southern California, and during our courtship, we sometimes drove to the top of that mountain from where we could see the whole Los Angeles area. It was a spectacular view. But it always gave me a bit of a thrill to see up close the observatory that housed the historic telescope that changed the way we look at our universe. For Hubble, in that very spot, not a great many years before, it was the first time any astronomer could see many galaxies. He was able to measure both their distances and speeds and verified Lemaitre's predictions. Hubble invited Einstein to Mount Wilson and finally convinced him that the universe was indeed expanding. Einstein finally caved in and removed the gravitational constant from his equations and called it the greatest blunder of his life. Now you would think that this evidence would convince the scientific community, but it did not. Controversy broke out, and most of that community would not accept these results. Physicists and mathematicians worked furiously to try to develop models of the universe that would save its steady-state nature. Why? Because the idea of an expanding universe implied that it had a beginning, a time zero. That came too close to the idea that it may have had a creator. And that was too close for many scientists philosophically committed to a naturalistic philosophy to accept. The steady-state universe allowed them to avoid the possibility of something outside the universe that had created ours. In 1964, 2 American radio astronomers, Robert Wilson and Arno Penzias, worked at Bell Labs in New Jersey and decided to investigate the electromagnetic radiation in the microwave range. Traditional astronomy looks for such radiation in the visible range, the radiation that we can see as light. But visible light is only a small part of the whole range of radiation, which includes X-rays, cosmic rays, and guess what? Microwaves, the same kind of radiation that heats your food in your microwave oven. So these 2 men built an antenna that would allow them to look at what was going out there in the universe in the microwave range. And all they got was a buzz, no matter where they looked. They thought that there must be something wrong with their equipment. They even removed a nest of some that some pigeons had built in their antenna, hoping it would give them more useful readings. It did not. They worked and got no better results. It finally dawned on them that they may have stumbled onto something much bigger than they had expected. So they started to record what they were gathering. It turned out to be a flood of microwave radiation anywhere they looked. It was perfect black-body radiation at a temperature of 2.725 degrees centigrade above absolute zero, equally present no matter where they looked. When they checked further, they found that this was the exact distribution of radiation that you would expect from a universe that started out as a superhot ball 13.8 billion years ago, the exact age of the universe that Lemaitre and Hubble had predicted. This was so impressive a finding that they won a Nobel Prize, and it finally settled all disputes about whether the universe had a beginning about that long ago. The controversy and how it ended is documented in a fascinating book by Robert Jastrow called God and the Astronomers. Now, Jastrow is not a religious person, but he saw what was going on. The progress of science is strongly influenced by the worldviews of the scientists doing it. We so far talked about how Newtonian mechanics had to be modified for long distances and very high speeds. But there were some other major modifications needed on the other end, tiny particles and very small distances. This is an area of interest that has turned out to be even stranger than relativity. I don't have the time to tell you much of the story, but here are some of the main conclusions from many experiments. It was found that in this range, first, particles sometimes acted like waves, and waves sometimes acted like particles. How they will act depends on the particular experiment they do. Einstein agreed with this, but we'll come back to him later. Another finding was that no matter how good your instruments are, if you know a particle's location, there's a limit on how well you can know its momentum. Likewise, if you know its momentum, there's a limit on how well you can know its location. This is called the uncertainty principle. This is not about your measurements. It's about what you can know even if you had perfect measuring instruments. Another finding was that in an atom or molecule, you can never tell where the electrons are. They don't move in regular orbits like planets around the sun. They jump all over. The best you can do is know the probability that they'll be at a certain point. Fortunately, it turns out that their location isn't that important, because if you can determine their energies, you can determine their energies without knowing their exact positions. All this is very strange. What it means is that you can never actually visualize what is going on at this microscopic level. Furthermore, even if you have instruments that could look down to that level, the very fact of looking at such objects would make them change where they are and how fast they're moving. In other words, there's a limit to even what you can observe. This is so wild and mysterious that the noted physicist Richard Feynman once said, "Anyone who thinks they understand quantum mechanics doesn't." That doesn't mean that it isn't useful. Surprisingly, it has given us a great deal of information about atoms, molecules, and electronics. But we can't visualize what was going on. All we have is equations. But fortunately, they tell us a lot. A good way of thinking about quantum mechanics is that it's like landing an airplane in zero visibility, having to depend completely on its instruments. One of the great ironies in science is that one of its most brilliant physicists, Albert Einstein, never fully believed in quantum mechanics, although he agreed with some small parts of it. Its statistical and probabilistic aspects offended him. In 1926, he strongly denounced it. His famous summary was, "God does not throw dice with the universe." That's all I can say about in the short talk about quantum mechanics and relativity, but here's where it leads. What we have in both these branches of science are equations. They can be run both forward and backward. When we run them backward using some astronomical observations to give us some guidance, we find that they can take us back almost to the very beginning of the universe, but not quite all the way. At some very early point in time, called the Planck time, which is about 5.39 times 10 to the minus 44th seconds. That means there are 43 zeros after the decimal point before the 5. The theories of relativity and quantum mechanics give us contradictory results. That means just as Newtonian mechanics was not quite right at extreme conditions, neither are these two theories. But what that means is that we can't know how the universe began, who or what caused it. Scientists are frantically working to figure out how to patch this up, so far with no success. But here is something sobering. Unlike the limitations of Newtonian physics, this limitation will likely never be overcome. Even if some bright mathematicians can construct a mathematical model that bridges the two, we can never test it like Einstein suggested ways to test relativity. The problem is that the energy required for any such test are nowhere available either here on Earth or anywhere nearby in space. So here's what this all means. If there is a Wizard of Oz behind the creation of the universe, he, she, or it has designed a universe in a way such that, first of all, we can know a great deal about it all the way back to a microscopic time from its beginning. On the other hand, the wizard has also disguised him, her, or self so well that we can never know what started it through science. We can never know whether he, she, or it exists, or if not, we can never know how the whole shebang called our universe got going in the first place. In other words, he, she, or it has revealed a lot, but has also hidden him, her, or itself in impenetrable mystery. Let me repeat in wrapping this up. I love science. I plan to give my life to its study. But I am also keenly aware that there's a limitation on what science can tell us, even about our physical world. And if it's limited there, how much more is it likely to be limited in telling us about our even more important personal questions? And what are we going to do about that? Next time, we'll talk both about where we're going from here, including what our options are to get answers to our bigger, although personal questions. But for today, some discussion questions are these. What do you think about all this? How does it make you feel? Well, good to be with you. I hope you'll be with me next time.